Okay, then the second half we goes to capacitorless LDO design. The motivations, I think everybody we mentioned just now, right? In the conventional PMIC, we integrate DC-DC converters, LDOs in one PMIC. One PMIC provide like 10 or 20 supply outputs or even more output to supply the SoCs. But it requires there's two problems with the conventional solution is it consumes too many pins, right? Another thing is if LDO is far away from the load, the performance will not be good, both for transient response and power supply rejection, right? If the capacitor or the on-chip LDO is very close to the load, then it can provide a better supply, right? In terms of ringing, supply ripple, noise, etc. Okay, so that's why we like, of course, we want to have a capacitorless LDO. But it imposes many challenges. We have some summaries later. It gives us a lot of challenges to get good transient response and good power supply ejection. And here is another classic paper which is called capacitor-free CMOS LDO with damping factor control technique. Actually, the damping factor control technique, frequency compensation technique, it's a alternative for nested emitter compensation. And it's in this case, actually it's used for the case with an off-chip capacitor. In this case, it can support the case with off-chip capacitor or without off-chip capacitor. Let's talk more about this. Here shows a three-stage design, three-stage amplifier or three-stage LDO design. If it is a nested emitter compensation and what we discussed last time, we will have the bandwidth degradation with more Miller capacitor, and because the two non-dominant poles are close together, if we have CM2, the bandwidth actually will reduce. If we don't have CM2, which means we don't have the nested Miller compensation, the two non-dominant poles will be very close to each other, and then we will see a frequency picking. The idea of damping factor control is to use in the scenario that with low power consumption and large load capacitor and high bandwidth. So how does it work? We have a circuit shown here. So the circuit in the blue box is the damping factor control compensation. It's basically a GM cell, okay? M9 give us the GM cell, the 1/GM impedance. The CD, the compensation capacitor here is to short M9 at high frequency. So M9 can give us 1/GM at certain frequency. And the other circuits from M10 to M15 is for generate the DC operation point of M9, right? So basically only M9 and CD is contributing to the compensation. The other circuit are DC for DC bias. And this entire LDO is a multi-stage LDO. It has differential input stage. It has a GM boosting stage, M7 and M8. So what is the GM boosting stage? In this case, let's assume M7 is 4 times larger than M8. M7 is 4 times larger. So if there's a small delta V on M7, there will be 4 times current difference. I mean, M7 is 4 times stronger than M8, right? So a small delta V on the gate of M7 will generate large delta V on the gate of M8. So it's amplified. And the good thing is it does not generate low frequency pole. It has one more stage, right? M7, M8 is they formed from gate to gate. We have one more stage. But this pole, the added pole is high frequency because here is 1 over GM. The pole, the resistance of this pole is related to 1 over GM, which is a high frequency pole. And M8 will drive, the voltage has been amplified, and the voltage goes to M19, and then for the common source stage of M19, it will drive the gate of the power transistor. And it has a meter compensation CM1 between output and the output of the first stage of the differential stage. And then on the right, we have the small signal model, Vout feedback to the first output of the first stage, and the damping factor control circuit give us, it will tune the relationship between pole 1 and the pole 2. In this case, output pole is the dominant case, actually. So it will reduce the damping, it will increase the damping factor. So to make the circuit more stable, reduce the peaking at the frequency domain. In capacitor-less case, so if this LDO don't have output capacitor, if we don't connect output capacitor, this LDO will shift to internal pole dominant case, right? Then the EA output or the differential amplifier output will be the dominant pole with meter compensation. Okay, and yeah, that will be the case. Another technique they propose here is to have a CF. The CF, I think in the next slide here, in this slide, is better explaining the effect of CF1. This is the feedback resistor ladder, RF12. So this capacitor is feed-forwarding the signal, right? Vout, the high frequency Vout can go through the capacitor to V feedback, give us a 0. But nothing comes for free. V feedback in this case will have a pole as well. So it's a pole 0 pair. But the 0 will be low frequency compared to the pole. So the 0 has a certain effect to the phase margin, and then we want the pole to be outside the unity gain frequency. So we don't want this pole, we want this 0, and 0 is relatively lower frequency because it's 1 over RC, and for the pole is is it? I think maybe it's a typo. Let me think. Okay, no. So the pole is at high frequency. We feedback related to the two resistors in parallel. Okay, so we can enjoy this 0 easily. So this technique can be easily used in any LDO that with a feedback resistor ladder. And this is open loop. This is another open loop LDO. It can be used in digital circuit systems that do not that much sensitive to supply. I mean, that's not very sensitive to the DC voltage of the supply voltage of the supply value. Here, it's a very stable. It's a very stable loop because here the V mirror is only a mirrored voltage of Vout, and the bias current is fixed. So this feedback loop is very stable. We only reuse a VG for the power transistor. The benefit is that it is very simple and it's very stable, right? Because the load variation will not affect the feedback loop at all. The drawback is the output voltage will change with load current when the load current increase, the output drops. But when the output drops, there's a benefit, uh, during with the DC load line technique, but this is not DC load line technique, right? Or the adaptive voltage positioning. We um, like high voltage, high output voltage at the light load. That means we have more voltage headroom for the LDO to drop, right? Then at heavy load, we have low supply. It has more headroom for the output voltage to go up for the overshoot. So in terms of load transient, this is a good phenomenon, right? For the DC load line, in some designs, we intentionally to make output voltage change with load current, right? That is good for load transient because we have more margin. We have doubled the voltage margin, voltage headroom for voltage undershoot and voltage overshoot. Another benefit, if it is a digital load, if it is digital load, at heavy load, we have low supply voltage. We make sure the low supply voltage uh, is good enough, is high enough to maintain the high performance digital circuit operation. It saves energy, right? It saves power. At heavy load, it consumes more power. When it consumes more power, it's using low voltage, which is good. And in light load, although we have high voltage, but the current is small. So in terms of energy efficiency, it's acceptable. So that's the considerations for the replica LDO. And the FVF LDO actually is also one kind of replica LDO. This Cascode-fvf was published by Intel 20 years ago. That it has a folded Cascode FVF, and the reset voltage set the output voltage, right? But it's better. This FVF LDO is better than the simple replica nmos LDO because in the nmos LDO, there's no local feedback loop, right? The output variation will be large versus load current. For the Cascode FVF, we have a local feedback, right? The Cascode FVF have a local feedback, although it's an open loop LDO, right? With Cascode FVF, we have one more pole compared to the conventional FVF or the basic FVF. It has one more pole and may be more difficult to be stabilized. We can use Miller compensation. If we want to set the dominant pole at the gate, then we need to have a Miller compensation capacitor between the gate and output. Okay, this is a widely cited paper, an output capacitor-less LDO with a Miller compensation. The output is here, and the middle part is the folded Cascode FVF with additional stages. You see, when we out feedback through M11 to M15 to M21, then it's a common source stage with a current mirror stage that drives the power transistor MP. So that's the main core feedback loop of the LDO. On the right, it's the DC biasing circuit that generates what we call reset. Here's the reset. Here's the reset. And the Vref is here, the reference voltage is here to generate V mirror and reset. For this local feedback, for the low frequency, local feedback, we have a C2 connected to ground that defined dominant pole of this DC loop, not this low frequency loop. For the FVF loop, the dominant pole is at the gate of M21, with this Miller compensation, Miller cap. It has a voltage spike detection circuit that enables pseudo class AB operation that is achieved by C1. Right? If we out have load transient, load variation, if we out have large voltage spikes, then the voltage change, the sudden change will be coupled to the gate of MB2. So MB2, let's assume V out increased. If V out increase, gate of MB2 increase, then more current goes through MB3, M16. You pull up the gate of M21, pull up, then it's less current, it will be less current to support to the Vout that has been higher than the standard value. Actually, this circuit, this example only provide one direction voltage spike detection or coupling, right? Actually, we can use another. Actually, if you consider the Miller cap as the transient response capacitor, it can help us to improve the transient response. Let's say if we out decrease, it through this Miller capacitor, uh, this node, the gate of M21 decrease, then we have higher current through M22, 23. You pull down the power gate of power transistor, it will have more current go to Vout. So this is also a fast transient response loop from Vout through the Miller cap to the current mirrors and then to the power transistor. And this loop depends on the rate of change, right? The faster the Vout change, the capacitor can better couple the variation to the gate of M21. So actually, in the later lecture, I call it's a derivative control, right? D control. In the PID control, it's the D control that give us faster transient response. So basically, for capacitorless LDO designs, we usually people set the dominant pole inside the amplifier or the feedback loop because we want the output pole to be, there's no large capacitor on the output, so output pole will be high frequency. And because we don't have large capacitor on the output, we need certain transient detection circuit, transient enhancement circuit, and also PSR enhancement circuits to maintain reasonably good performances. The output capacitor is actually important, really important to LDO designs. The FVF LDO can also be driven by current mirror type buffer, right? Like we mentioned, if we want to have good PSR for the power transistor, if we have a current mirror buffer, then this VG will follow the change of VDD, which can actually give us good PSR. The problem is the voltage headroom, because actually the FVF has certain issue with the voltage headroom because this node cannot be high actually, right? Because its VDD minus VDS minus another VDS goes to this node. And this node is actually to the gate of the power transistor. That means if VG cannot go high close to VDD, we cannot completely turn off MP. That will have leakage current or we cannot operate this in no load condition because this node cannot go to high voltage. So that's the trade-off here. So we may need more sophisticated circuit. We cannot simply use this one. This one cannot turn off the power transistor because this node cannot be high. And we can have a enhanced current buffer that that have a RC circuit here to I mean to have a to maintain the bias current here, right? Here M2 also provide the operating condition of this branch. If we out decrease, then this node decrease, we want to discharge VG faster, and we don't want M2 current to change fast. So in such case, we can have a better response to the load. We can have adaptive biasing with this configuration, but it will change relatively slower because it goes through an RC circuit. Yeah, I think we need to have more careful considerations when we do such adaptive biasing here.